So it is the 26th of April, 2018. And we're talking about dogs. And I've got this particular dog here, and I'm going to actually copy this dog over. So I've got 2 of these dogs. And maybe we'll make 3 of these dogs. What the heck? How many of you have ever stared deeply into a dog's eyes? I'm going to assign you homework. You should go sit and stare deeply into a loving dog's eyes. You just haven't met the right one. And absorb some of that dog energy. It's a good thing. It'll soothe your soul. It'll make everything okay for a moment. Now, when you're staring into that dog's eyes, a lot of dogs have got, well, yes, they will stare back, have got pretty brown eyes. My current dog, we sometimes call her the amber-eyed imp because she's got the prettiest sort of golden, like copper-colored almost eyes. They're beautiful. And I've seen dogs that have really, really dark brown eyes. You know, sort of like dark chocolate. Lovely. Yeah. But among huskies and Australian shepherds and Catahoula leopard hounds, there is a mutation that occurs, and sometimes you get, and boy, are they pretty. You get dogs with blue eyes. Oh, they're pretty. They're haunting looking. Gorgeous. And if you're a breeder, the blue-eyed trait is pretty valuable. I think my understanding is that, especially with Catahoulas, I don't know if it's true with Aussies, people will pay more for a puppy with the blue eyes. So if you're a breeder, would it make sense to ensure that as many of your puppies as possible had blue eyes if you want to maximize your investment? Yeah. Oh, well, in order to do that, you kind of need to understand genetics. I don't know if this is this a single gene mutation? Do you know? Is it monogenic? We'll have to look it up. You don't know? Okay. So we'll look that up. I'm not sure if this is monogenic or polygenic. Of course, eye color in humans is polygenic, but pure blue eyes are a single gene mutation. So if you wanted to ensure the highest proportion of blue-eyed pups among the litters that you're producing, you would want to trace that trait among your pups and their offspring. And the way we trace a trait over many generations is called a pedigree. Pedigree. Some of you have seen this term. And a pedigree is just a way to trace a trait over generations. And this is a very standardized format that's used. Should any of you ever decide to reproduce, depending on where you are when you reproduce and what hospital you're going to and who your doctor is, they may order genetic testing. If you have a family history of certain diseases, somebody will sit down with you and do a pedigree to try to figure out if you should be concerned about your offspring. If you are breeding dogs, you're going to have a pedigree of all those dogs' ancestors so that you can trace the traits that are present in them. If you have show cattle or show horses or show goats or show bunnies, you're going to have pedigrees behind them. Though the kind of pedigree we're talking about here is actually a visual representation. It's like a map of multiple generations. So the pedigree format is very, very standardized. You are going to draw them. You are going to draw many of them. And then you're going to learn how you're going to use them to interpret a family's history. So at the very simplest, a pedigree is squares and circles. And the squares are males. The circles are females. And when we connect two individuals with a line running between them, connecting them like that, it's called a marriage line. It really just means reproduction. If we're tracing non-humans, of course, we don't know that non-humans have anything that we would call a marriage, but they certainly do reproduce. And you don't have to, this may come as a shock to you, you do not have to be legally or religiously married in order to reproduce. Perhaps you're aware of this. So that line, it's really a reproduction line. Now, we sometimes show it if two people have partnered, if they've married in some way, even if they haven't had offspring yet. But it's really showing that these two people are going to reproduce or have reproduced. Because then what we do is we drop a line down from that couple and we can show their offspring. So this couple has an only child who is a what? Daughter or son? Yeah, they have a daughter. They have one daughter. We'll move them over here. And we'll put another couple up here. Male and female. Questions? So we've got this other couple. We're going to drop a reproduction line down from them, and we're going to give them 3 offspring. What do they have? You have a question?
No. Mom was just yelling at me because I drew 3 kids and the first time when you only drew 1.
That's fine. It's okay. Okay. Now, ideally, we would have all of our generations neatly lined up. Oops, I don't want to do that. We would have all of our generations perfectly aligned. But well, it's always a little rough when I start off. So we can realign. I'm going to move these guys up. And extend that line there. Okay, because what we want to be able to do is label our generations. So this is the first generation that we're dealing with there at the top. We have the second generation here. Can you predict what's going to happen? There's going to be a 3rd generation. Oh, look at that. Hey. They just reproduced. I'm going to give them a daughter. And, ooh, what's this? What's this? Twins! Whoops. I'm not going to color that in yet. Twins! They're coming off a single stem. Some sources, there are 2 ways to show twins. I want to tell you about this. So we can show twins. That's sort of, I call it the cherry stem. And then there are sources that will show this for identical twins. There are other sources that will show that for identical twins. Obviously, if one's male, one's female, they cannot be identical twins. They're fraternal. Do you know that twins are called mono and dizygotic? Mono means how many? 1. Zygote is a fertilized egg. Monozygotic twins came out of 1 egg. Single egg, fertilized, split at some point. 2 humans. Dizygotic or bizygotic? 2 zygote. 2 zygote twins were because 2 eggs were released at the same time and they both got fertilized. So those are the fraternal twins. You can have a boy and a girl. You can have fraternal twins who look a lot alike and are the same sex. And then it gets tough to tell. Because you can have siblings born years apart who look a lot alike. So you can certainly have siblings conceived at the same time who look a lot alike. Okay, so great. We've got a 3-generation pedigree. Now, why are we doing this? Oh, we want to trace a trait. That's right. So we could be doing this pedigree about animals. We could be doing it about humans. But we'll go ahead and stick with humans. And the other important thing to know is that we also use squares and circles that are colored in. Not dead, no. Affected. Well, affected with whatever the trait is. They could be affected with blue eyes. You know, whatever trait we're studying, the colored circles represent it. So I'm going to tell you more fun facts. I have crooked pinky fingers. Everybody, oh, you have hitchhiker's thumb. Cool. If you look at your pinky finger, some people's form a straight line when you hold them up like this. Some people's look like a crook neck squash. This is a single gene mutation. It is considered, I mean, my God, it's like the mildest of possible birth defects. It's considered a very mild birth defect. I found this out as an adult. I was traumatized by my fingers the whole time I was growing up. I would look at them and think about how hideous and how ugly they were. And, you know, was there something I could do about my hideous fingers? I should probably just be shipped to an island by myself because I'm obviously a mutant of some sort. No. Once again, get over it. You're all fine. You're lovely people. This is a single gene mutation. We could track crooked pinky fingers in a family.
Mine's not crooked.
No, yours is beautifully straight. You could be a hand model. You could have rings on your fingers and they'll take pictures of them. Anybody else in my crooked pinky club?
Is this crooked?
Let me see. Well, it's crooked this way. Looks like a summer squash this way. Nope, yours is straight. Yours is straight. It's called crinodactyly, I think. It's because the middle bone in the finger, instead of being a perfect rectangle, is triangular. I know, how weird is that? So anyway, other than the fact that you can never be a professional hand model, it really doesn't impact your life in any way. So let's go ahead and we will trace crooked pinky fingers in a family. So this is an imaginary family. I made them up. Good, zoom tight. Okay. There's my pedigree for crooked pinky fingers.
Wow.
Clinodactyly, that's it. Clinodactyly. Dactyl refers to fingers. First question we want to ask ourselves when we look at a pedigree is, do we think this trait is autosomal or sex-linked? Do we think it is recessive or dominant? So at your tables, talk. Is this trait autosomal or sex-linked? First question. So here's a set of questions that we want to ask. Okay, so if we want to examine whether this is sex-linked or recessive, what did we find about sex-linked traits? Do they predominantly affect one sex over the other? Yes. Who do they predominantly affect? Males. Sorry guys, yeah, males. Pretty uncommon for a sex-linked trait to affect females. Do you see this being affecting both males and females? I see 4 females and 3 males who are affected over 3 generations. So the question is, you know, does it matter that it's both females that are affected in the first generation? Well, no, it really doesn't. So this female passed her, whichever gene it was, on to this daughter, and that's the only offspring she had. We don't know if she had had 10 sons, what would have happened. She only had 1 daughter. That's the data we've got. This female, though, passed this gene on to both a son and a daughter, and they were affected. Now, both these parents had whatever gene this was, and they passed it on to their twins. They did not pass it on to their daughter. So, does anybody want to revisit their assertions about sex-linked or autosomal?
I want to change my answer.
Okay, that's what I'm saying. This is pretty clearly autosomal. This is not sex-linked. Yes, ma'am. The question was, because we have those twins down there, could only one twin get it? If those twins are the product of a single egg and a single sperm, they are monozygotic, they are identical, they have identical DNA. Neither of them can have a genetic condition without the other one having it. If they are fraternal twins, 2 eggs, 2 sperm, they are no more related than any other 2 siblings. They just happened to have been womb mates. Get it? Womb mates. They were in utero at the same... Okay, it's funny. Womb mates. They shared a womb. Ah! Yeah, okay. So now the next question, and this is the tougher question. Is this condition dominant or recessive? Talk at your table, convince one another. So we know it's autosomal. So this is a tougher question, and what we have to look at, let me get rid of all my little circles and arrows here. what we have to look at when we ask this question is it's kind of like it's kind of like proving a negative. Do you see in any generation there an offspring who has the trait when neither of their parents are affected? So if you ever see that pattern, you know immediately it's recessive. We don't have that to go on. So the question is, well, what would the genotypes be? Let's go into this assuming, because we don't have the one piece of evidence that would say that is definitely recessive. So let's go into this assuming that it's dominant, and let's run the problem and see if it works. So I'm going to get rid of the sex-linked part. We know this is autosomal. So now we're just down to deciding if it's dominant or recessive. And we're going to use big N, little n. And this is pretty common when we're talking about medical conditions or any kind of condition where N is normal, or actually, you know what we should use here? We should use big A, little a, because we're assuming that we're running this as if this is dominant. So we're going to try it out. So then this would be affected. This would be not affected. So if that was true, okay, so let's list our 3 possible genotypes. What are our 3 possible genotypes? List them, write them. We could have big A, big A, little a, and we could have little a, little a. So then what would the phenotypes be that were associated with those? 2 of them are affected. So if that's the case, is there anybody in this pedigree whose genotype we immediately know? Yeah. If that's true, whose genotype do you know? Do we? Whose do you know?
Would we know like all the white ones?
We would know all the people who weren't affected. Because if this is dominant, then every single person who's not affected has the same genotype. If you get a pedigree problem on the air test, you get a piece of paper, you list all the possible genotype combinations, you list all the possible phenotypes, then you try to interpret that. Don't try to do it off the cuff. Don't try to do it off the top of your head. Write it out. Okay, so if that's the case, then we would say that this is AA, this is AA, this is AA, little a, little a, little a, little a. Do we know the affected individuals' genotypes? We have it down to 2 choices, right? Okay, so we know that this one is either big A, or big A, little a. I put an E. That was stupid. There. That's better. Now, do we know her genotype? Let's do a Punnett square between her parents. She has to be big A, little a. Why? Because her dad didn't have a big A to give her. Ah. You look back at Dad and you're like, well, she had to get a little a from Dad. We know that. So we absolutely know for certain that she has to be big A, little a, if this is a dominant trait. So do we know his genotype? Big A, little a, why? Same reason. Look at his dad. So we know he had to get at least one little a from his dad. Now, let's do a Punnett square. Let's do a Punnett square between this person, whoops, this person and this person. So what we want to ask ourselves is if our hunch is correct and this is a dominant condition, and we've got those genotypes for that set of parents, are those offspring a possible outcome of this being a dominant condition with those parents? Well, we have a 25% chance that they'll have a double A, little a, and sure enough, they do. They have a 75% chance that their kids will be affected by this. You know, in essence, in one conception, if we're assuming, well, maybe those are, I guess those are non-identical twins, so they would count as just siblings born at the same time, womb mates. So then 2 of their 3 kids are affected. You know, is this possible with the Punnett square we've got for them? Yeah. I think it's a pretty good bet that this is an autosomal dominant condition. So we'll get rid of the or recessive. And there have been questions in the past on error tests where they give you a pedigree and they say, you know, first of all, is this sex-linked or not? Second of all, is this autosomal or sex-linked? Is it recessive or dominant? Because there are both autosomal dominant conditions and there are autosomal recessive conditions. I don't know of any sex-linked dominance. All the sex-linked conditions I know of are sex-linked recessives. Let's do one more. We've got our second one. Same question applies. Is this autosomal or sex-linked? Is this dominant or recessive? 2 sexes that are affected in this pedigree. Anybody want to change their answer? You think this is sex-linked or autosomal? Autosomal. In general, like we said, you can have females who are affected by X-linked traits, but it is so rare. Yeah, you would not find 2 out of the same family, you know, because it's kind of a 1,000,000 to 1 shot. It happens, but boy, is it rare. Okay, is this recessive or is this dominant? Why? In every case here, we have children who are affected born to parents who are not affected. Now, you can have an affected parent who has an affected offspring if they marry a carrier. We're going to get into that in a second. This is a autosomal recessive. So if this is a recessive, we're going to use big N, little n, where big N is not affected. And 2 little n's will get you an affected phenotype. So the possible genotypes are big N, big N, big N, little n, little n, little n. Bingo. So these guys would have a phenotype of not affected. And the affected individuals would be little n, little n. So can we label anybody's phenotypes? Yep, we sure can. Little n, 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 little n. Now, what you're not aware of is that there are 1, 2, 3, 4, 5, 6, 7 other people in this pedigree whose phenotypes we know 100% certainly. So let me tell you a story about a girl I went to school with. Carrie was 2 years younger than me, a year or 2 behind me. Her sister was in my grade, and you know, as kids, you don't know much about anybody. All anybody knew, I think, about Carrie was that she was super, super skinny. She was like the tiniest, frailest, skinniest little thing Like you could just about see through her. And she missed a lot of school. And she sounded like she had a smoker's cough when we were in like elementary school. She had a disease called cystic fibrosis. She was born in, what, 1970 something? No, she'd be younger than that. And CF is a disease that, it's a single gene mutation. I forget what the percent, like 1 in 112 humans of European ancestry carry this gene. They're not affected, they're a carrier, so they're this. And prior to the 1940s and 50s, kids with CF just didn't live long because their body produces an abnormally thick mucus which coats the inside of the lungs, and it traps bacteria really effectively. So people with CF are really prone to respiratory infections. It also coats the inside of the digestive tract, and that's where you absorb nutrients and calories. So people with CF can eat as much as you or I, but their body can't get the nutrition out of it. So they don't gain weight. So as somebody who has never had a problem putting on weight if I wanted to, heck, I've usually put on weight when I didn't want to. It sounds like a great thing to me. Eat whatever you want, never put on a pound, awesome. No. Because we're talking about babies who won't gain weight, babies who won't thrive, babies who will die because they're not getting nutrition. So their older daughter, Chrissy, was born, and she was a normal, healthy kid, and everything was great, and she was 2 or 3, and her sister came along, and she was a small little baby, and then she had problems nursing, and then she was having respiratory infections, and she wasn't gaining weight. And so you bring home a baby who's, you birth a baby who's 7 pounds, and by the time you take her home, she's 6.5 pounds, and a month later, she's still under 7 pounds, and that's not supposed to happen. That's dangerous. That's serious. And I think she was like 6 or 7 months old when they got a diagnosis that she had CF. Well, her parents were just gobsmacked because they had never heard of it. I had no idea what they were talking about. How could she get 2 recessive genes? Where did she have to get one of them? Where do you get one of each set of a pair of alleles? From yo mama. Where do you get the other one? From yo papa. I want you to repeat that to yourself every time you look at a pedigree. Oh, you got one from your mama, you got one from your papa. So, the parents of these 2 individuals have to both have what genotype? Big N, little n.
Wow.
So every time you see a pair of parents who have an affected offspring with a recessive trait, guess what? They are both carriers. So these guys are both carriers. This one's a carrier. And that's when Carrie's parents found out that they were both carriers. Now CF is, there are some recessive conditions like my stupid pinky fingers. Okay, I can't be a hand model. Woohoo, I'm fine. And I'm not sure if this is dominant or recessive, I forget. There are some recessive conditions, yeah, okay, whatever, it's fine. CF is a little different because when you have a child with CF, you're going to watch that child go through tremendous pain. It is going to sort of engulf your whole family. I mean, there's daily treatment. It's better than it used to be. People with CF used to, like I said, they used to die in childhood. They used to not make it past 4 or 5 if they made it that far. And then by the time, when I went to school, who was in school, she said, well, I never really figured I'd make it to college. I didn't think that was going to happen. Because she kind of assumed that she'd be dead by 20. And, now there are people, and she came in and talked to a class of mine 5 years ago, and she said, I'm so happy because I work with a charity that takes presents to patients with CF in the hospital, and I bought a present for a 65-year-old CF patient. She was thrilled. Because the woman I went to school with is now in her 40s, and she's still alive. She's doing pretty well, considering. She's got a chronic health condition. She manages it every day. If you find out suddenly that you're a carrier for a disease like that, you begin to seriously consider if you want to have any more biological children. Her parents decided not to. They adopted 2 lovely little boys after the girls were born, so they had a family of 4, which was what they were hoping for the whole time. They just did it differently. After the test, you're going to do a genetic counseling project where you're going to get case histories from families, and you're going to have to give people advice. Ooh. Don't worry, they're not real families. But there are real, honest-to-God people who work in hospitals who do that, who work with genetic testing and work with pedigrees to figure out what the odds are. Now, let me ask you this. I want to look at this guy. What do we know about him? Do we know his genotype? He's not affected. None of his kids are affected. What do we know? Why is he a carrier? He is. He is 100%. There is no doubt about it. He's a carrier. Why? Where did he get one of his copies of his gene? From his papa. And his father only had small n's to give. Okay? There are people on this chart we cannot be sure about. We don't know about her. She's a question mark. She could be big N, or big N, little n. Same for these. We don't know. We're not sure. Yes? Which one?
Never mind.
Okay. Okay, is the sex-linked or autosomal? You guys say sex-linked because we're only seeing affected males. Is there some slim percentage chance that through random luck of the bad luck draw, you could have a non-sex-linked condition that showed up like this? I suppose, but the odds are pretty slim. When you see all males affected in a pedigree, you should assume sex-linked, unless you have proof otherwise. So, sex-linked genotypes are a little bit different, if you remember from your homework last night. So we're going to use X big N and X little n. X big N, X little n. There is nothing on the Y. What are our possible genotypes for females? Well, she can be X big N, X big N. She can be X big N, she can be X little n. Are any of those females going to have an affected phenotype? Nope. She's got a spare tire. Gentlemen are running down the road with no spare in the trunk. All right, males. Possible genotypes, X big N, Y. Is he affected? Nope. We're assuming this is a sex-linked recessive. X little n, Y. I screwed that all up. Okay. Now, are there any males? Well, I'm sorry. Is there anybody on this pedigree whose genotype we 100% know? What about him? And his uncle? And his great-uncle? And his other great-uncle? They all share a genotype. What do they have? What do they have? They have X, little n, Y. Because they're affected males. And they only have one copy of the X chromosome. So we know that they got the bum copy. And this could be color blindness. This could be male pattern baldness. This could be something more serious. There are some fatal diseases that are X-linked recessives. Some forms of muscular dystrophy. Now, is there anybody else on here who's, oh shoot, that's what I didn't do. Let me actually give him a daughter. Okay, is there anybody else on here? There's a reason for that. Is there anybody else on here whose genotype we 100% know? Oh, where did all these affected males get that X chromosome? From their mama. They got it from their mama. Why didn't they get an X from their papa? Because if they did, they wouldn't have a penis. If they got an X from their father, they'd be a girl. They got an X from their mama, they got a Y from their papa. Therefore, no spare tire. So we know that every single one of the mothers of an affected male are X big N, X little n. This is what I did for my now mother-in-law the first time I met her. Hi, I'm dating your son. Can I do a pedigree and a couple Punnett squares for you? It's really cool. I'm so excited that he's colorblind. I think that's just neat. They fed me dinner anyway. That was nice of them. That was nice of them, yeah.
That's all I know.
I'm just here for the dinner. Okay. We know her, X big N, X little n. Do we know the unaffected males' genotypes? Sex-linked ones are so easy. Yes! Because they obviously have a normal X, or they'd be affected. So we could fill in all of those. Now, are there some of these women, do we know hers? No. We know her brother is colorblind. We'll assume this is colorblindness. She could be a carrier. We know her mom was a carrier. She had 2 sons. Neither of them are colorblind. Does that mean she's not a carrier? No. She could have just gotten lucky. Not that colorblindness is a big impediment. You can't be a fighter pilot if you're colorblind. It's not the end of the world. I can't be a hand model. My husband can't be a fighter pilot. Oh, well, there go our dreams. Do we know her genotype? So, where did she get? So we know that she's X something, X something. We can show adoption, we can show surrogacy, we can show all kinds of things on a pedigree. We'll go into all that. I've looked it all up over the years. Okay, where did she get 1X? From her mama.
I bet you I know.
Where did she get her other X? Mi padre. Which X did her father have to give her?
The second one.
The bum X, the defective X, yeah. The little n. Guess what? If you are the daughter of a colorblind male, there is a 100% chance you are a carrier for colorblindness. Very often, colorblind males, upon asking a few questions, will discover that, oh, Grandpa was colorblind. Well, yeah, and Grandpa gave his bum X to your mother, who gave it to you. So, before you leave, you will have homework. You have a worksheet to complete, which I already copied, and I'll find for you in a second. And you've got a couple of play pause.